we can start now. 9 a.m. Monday. And in this class, we're going to discuss practice Gauss's law, right? We introduced it in the previous lecture. It's basically one of the fundamental laws in physics, right? So it means that you can apply it at any point of the universe, at any moment of time, and it should work. So far, no one has managed to see an example where it doesn't work, right? So now, as a result, so it cannot be derived, so we just need to introduce it and practice how to use it, right? So let's assume that we have this distribution of charges, completely arbitrary. And, okay, Q1, Q2, Q3, all the way to Q5. And what if you pick a closed surface? We discussed what closed surface is, right? So let's assume that you picked a closed surface, which we're going to call Gaussian, right? And if you count electric flux through that closed surface, right, electric flux, then that electric flux must be equal to the total charge inside of the Gaussian surface divided by the constant epsilon naught, basically this, right? So this left-hand side of the Gauss's law, integral over the closed surface E dot dA, it's the electric flux. Maybe I should add also, so it make it clearer. So that is electric flux, the left-hand side. So the flux integral, this integral over the closed surface of the Gaussian surface must be equal to the total charge inside of the surface divided by epsilon naught. Okay, Gaussian surface, it's a pure imaginary concept, right? It doesn't mean that there must be some surface over there. No, you just decide by yourself, right? Okay, this is my Gaussian surface and I'm going to use it in my Gauss's law, right? All right, and then distribution of charges doesn't matter. For example, this charge Q1, you can move it over here, right? Position over there, and the law will still look the same. Just as long as the charge, or a charge, as long as a charge within the Gaussian surface counted in towards the total Q enclosed. All right. Okay, it should be enough, and now, yeah. Of course, most of the time we use Gauss's law to find the electric field, right? And yeah, it's a great law, universal law, but the problem is electric field is buried inside of the integral. And every time if you want to find electric field, you need to somehow extract it. And of course, it can be quite complicated procedure unless there is a nice symmetrical distribution of charges. And that's what we're going to discuss in this course. We're not going to discuss some complicated electrical systems. No, distribution of charges will be nice. In the lecture, we started discussing spherical distribution of charges, right? And we wanted to find electric field outside and inside. In today's class, we're going to discuss cylindrical distribution of charges. We will have some cylinder uniformly charged, and we will have to find charge inside and outside. But before we start discussing cylindrical surface, let's look at the conceptual question 6, CQ, conceptual question. So it's a chapter 24, still chapter 24, conceptual question 6. So what do we have? We have this distribution of charges, and the book offers us to discuss a few Gaussian surfaces. And we need to calculate the electric flux. Okay, let me write, it's very important. So we need to find electric flux, right? So not the electric field, electric flux. And first is surface number 1 is on let's assume it's this one. Okay, so let me label it surface A. Sort of three-dimensional, but of course I draw a two-dimensional picture only, right? Okay, so what will be the flux through surface A? Okay, I will remove that subscript E and I will just use subscript A. Okay, you understand it's still electric flux through the surface A. This problem, this question is trivial because the question is not about finding the electric field. Yeah, that will be complicated, okay, reasonably complicated, right? The question is about finding the electric flux. And the electric flux, it's the whole integral. So it means that you don't have to extract the electric field. So this whole left-hand side is the flux. So in our case, we just need to calculate total amount of charge inside and divide it by epsilon naught. That's it. So these questions, banal. Right? Sometimes I give a question like this among multiple choice questions on the exam. Right? So in this case, it will be, okay, let me write Q enclosed over epsilon naught. And in this case, we have plus 3Q and plus Q. Plus 3Q plus Q divided by epsilon naught. So the flux will be for Q over epsilon naught. Only charges inside. Any charges outside, we don't care about them. They are outsiders. So then, B. The second surface is B. Let's say this one. Yeah, I need to label it. So let's say surface B. Again, the same. So what's the flux? Electric flux. So in this case,
-4.
yeah. So minus
-4.
Q, yeah, absolutely. Minus Q minus 3Q over epsilon naught. So you see, the questions about the flux are trivial. Now the last surface, let's look. And then probably let me pick this surface. So surface C. Flux through surface C will be, you should be able to see immediately what will be the flux. Of course, 0, right? Minus Q plus Q, of course, 0. Right? Okay, and there are a few, like 2 extra surfaces, but you got the idea. So after this, it's a bit of cake. Again, the question is about finding the electric flux. In this case, it's very, very simple. Enough of that, and now let's start discussing cylindrical symmetry. Okay, so physical situation. We have infinitely long, okay, I couldn't find anything better than this paper towel, right? Infinitely long, uniformly charged cylinder, infinitely long, and with uniform charge distribution. And in this problem, let's assume that surface or volume charge density is given. Okay, let me draw this situation. All right, so it's effectively problem 2450. All right, 2450. All right. Okay, maybe I will write infinitely long, uniformly charged cylinder. Right. Okay, let me estimate the amount of space I might need. All right, probably I will start at this level. Yeah. Whoops. Okay. It's a physical surface, uniformly charged. So let me draw a few pluses. Let's assume it's positively charged. Right. Then what is given? A radius, r capital, right? R, and volume charge density. Since this cylinder infinitely long, we cannot talk about the total charge. Of course, in real life, nothing is infinitely long. Of course, it has ends. Of course, with a very good approximation, very often we can treat some object as an infinitely long, uniformly charged object. So, rho volume charge density. these two parameters are given: radius and rho, volume, charge, density. Okay, and so now we have, as I mentioned in the lecture, now we have two approaches that we can take. We can take either Coulomb's law to find the electric field, like when we integrated to find the electric field created by a charged ring. It's one approach. Or now we have Gauss's law. Two equally strong approaches can be used to find the electric field. But the approach based on Coulomb's law, in this case, it's not the most efficient way of finding electric field. It's still possible, but it will be more complicated. So let's try to use Gauss's law in this case. So Gauss's law, and of course I will write it underneath. All right, so again, I'm trying to estimate the amount of space I need. Okay, so integral of E dot dA equals to Q enclosed over epsilon naught. I just rewrote it, right? And what should be the first step? Without that step, we wouldn't be able to move any further. The first step must be Gaussian surface. We must to pick a Gaussian surface, because integration over what? It's a surface integral. It's an integration over a Gaussian surface. If you haven't picked the Gaussian surface, then there's nothing to discuss. And also Q enclosed. It's a total charge within the Gaussian surface. If you haven't picked the Gaussian surface, again, there's nothing to discuss. The first step, we need to pick a Gaussian surface.
Is that dA?
Yes, it's a dA.
Okay.
I just rewrote Gauss's law, nothing else. Right. Okay. As I said, you can use any Gaussian surface. No, first of all, where should we pick? Where should we choose the Gaussian surface? You know, in part A, this should be a part A. Let's find over here probably. We need to find, no, I will write it above this. Let me write above. All right, so part A, we need to find electric field outside. Basically where where radius r small is larger than r capital. Right. So part A. And so now we need to pick a Gaussian surface. First of all, Gaussian surface must be in the region where you want to find the electric field. Right? So if we want to find the electric field outside, so the Gaussian surface must be there. Because if you try to use Gaussian surface inside, it's sort of like a exploring life, I don't know, of Austria by going to Madagascar, right? So, of course, if you're interested in the electric field outside, of course, we need to pick a Gaussian surface over there. Then second, as I mentioned in the lecture many times, you can use any Gaussian surface. There are no restrictions. You can pick any surface you want, right? And you will be correct. I will never be able to tell you that you are wrong deciding to use this or that surface. But the question is, yeah, you can pick a very complicated surface, and of course you will be correct, but you will never be able to solve the problem. You will never be able to find the electric field. What's the point of being correct if you cannot reach the goal, right? So of course you need to pick the best possible surface so that you can use the symmetry of the problem, and we have cylindrical symmetry of the problem, right? So the best surface in this case is the cylinder of finite length, of course with radius larger than r capital. So the Gaussian surface, the best one, will be this. Of finite length L. L is not given. I just need to introduce this some kind of constant in the problem. And of course, I hope that at the end it will disappear. Right? Okay, over finite length L, and of course, some radius are small. So that's the Gaussian surface. Okay, let me probably show it here somewhere. So that's our Gaussian surface. Radius are small, length L. Again, it's basically our imagination. It doesn't mean over there must be some Gaussian surface. No, we're imagining it in order to probe the electric field in that region. So the first step, we picked a Gaussian surface. So now, this Gaussian surface has reasonably complicated shape, right? And we will, of course, we will have to integrate. We're going to find the net electric flux through that surface. In order to take this integral, of course, we need to split this surface into 3 parts. I doubt that you would disagree about that. Of course, we'll have to pick surface number 1. It's a cylindrical wall. Then front facet and back facet. So there will be 3 surfaces, right? And of course, this integral, we have to split into 3 integrals. We didn't do in the lecture when we have spherical symmetry, because in that case, the whole surface has spherical shape, right? Spherical type. But in this case, yeah, in order to integrate it, we need to split into 3 surfaces. Okay, so now let me do that. So now I start evaluating this integral. And then I will start looking at the charge, enclosed charge. So E dot dA. You remember that circle in the middle means that we are integrating over a closed surface. So, okay, let me label these surfaces first, probably. Let me label this surface as, this wall as S1 wall. Then this surface as S2 front. Let me first label. And this surface S3 back facet. Right. So 3 surfaces. And now, yeah, I can write the integrals, 3 integrals. Integral of E dot dA over the surface S1, this wall. Then probably I will leave some space. I will write the second integral plus E dot dA surface S2, the front facet. Integral is an additive thing. You can divide integral into as many integrals as you want. And plus integral of E dot dA S3. Okay, 3 integrals. Simple question in terms of mathematical question. Look, guys, here we have integration, and I use small circle in the middle. Why didn't I use small circles in these 3 integrals? And the answer is quite simple. Because when you collect these 3 surfaces, you will end up with a closed surface. That's why I added circle in the middle. But once you split the surface into 3, so this front facet by itself, it's not a closed surface, it's an open surface. So that's why circle there is not needed. The same cylindrical wall by itself, of course, it's an open surface, it's not a closed one. And the same the back facet, right? So that's why I didn't write any circles in the middle. Now let's evaluate these 3 integrals, and let's start with the maybe with the last one, S3. Right. So let's draw area vectors. These, and these. Right. Area vectors, and I will use green, right? So let's start with this, dA. I will take a small patch on that cylindrical wall, right? And of course, direction of the area vector, you remember the conventions. First of all, area vector must be perpendicular, right, to the surface. Second, must be perpendicular. Second, it must point towards the outside. You remember at the end of the previous lecture, we were discussing this convention. If you work with the closed surface, area vector must point towards the outside, according to the convention. Right? Okay, so in this case, towards the outside, it's radial, right? Okay, let me draw it. So this is dA. All right. Then let's draw area vector for the front facet. Front facet, again, must be perpendicular. Okay, it's this side, right? Must be perpendicular, right? And towards the outside. So it means that way. Okay. So this will be, okay, if I take yeah, let me take here a small patch, and this will be dA. And the same about back facet, back side. If I take a small patch over here, a small area, it's a back facet, right? So area vector, again, will be towards the outside. It means now to the right, here to the left, right? Okay, so now we have area vectors. Again, if something is still not clear, tell me. I'm trying to be as thorough as possible. But right now I'm talking about, yeah.
Will the magnitude of each of these three different dAs be the same?
dAs, it's infinitesimally small, so uh, we can talk about only if you integrate, if you calculate areas, right? At the end, yeah, the areas will be different. The dAs, you'll take infinitesimally small. I cannot compare infinitesimally small things, right? They're smaller than anything else. It's basically, it's almost like a point objects. I cannot tell which point is larger, which point is smaller, right? So that's why your questions kind of confused me a little bit, because now I'm thinking, what should I say, right? We cannot say which point is larger, which point is smaller, right? So it's an infinitesimally small object. I can tell that, of course, the total area of this surface, S2, will be, of course, different than the total area of S1, right? That's what I can tell for sure.
Okay.
Right now, it's not
Okay.
important if they're different in magnitude or not, right? Okay, so now next, now we need to know direction of the electric field, and usually books usually say something like this: because of the cylindrical symmetry, the direction of the electric field must be radial. Okay, yeah, I can buy, but it's better to justify it. And let me justify direction of the electric field over there. I will erase probably that side. Yeah, sooner or later, anyway, I will have to erase this. And I will write, so, justification of E direction. Right. Justification of E direction. Like I've done in the lecture. Okay, so let me draw our infinitely long charged cylinder. Now let me draw just a small picture. All right. Right. So I just redraw. And let's say we want to find electric field at this point, the direction of the electric field at that point. And let me draw auxiliary line, which is basically perpendicular to the axis of the cylinder. And now, since this cylinder is uniformly charged, of course I can all the time I can find, for example, I can pick a small point charge over here. Of course, this small point charge, okay, just point charge, is going to create an electric field which I can draw like this. But at the same time, this is infinitely long, uniformly charged cylinder. Of course, I can find all the time for any charge on this side, I can find symmetrically positioned charge. Again, symmetrically relative to this line, right? So this distance and that distance are the same. Of course, all the time I can find symmetrically positioned point charge on that side. And what will be the contribution to the net electric field at this point from that blue charge? It will be something like this. Of course, the same in magnitude, because I just picked the same charges in magnitude. So now, of course, I can, if you add them up, of course, the net electric field will be straight down. That is radial to the cylinder. So basically, using the symmetry, I can tell if you are going to integrate to find the net electric field, all the time horizontal components of the electric field will be cancelled. For any charge on this side, I can find symmetrically positioned charge on that side, and the components, horizontal components, will be cancelled. It doesn't matter which charge you pick, every time I can find symmetrically positioned, and horizontal components will kill each other. Only radial components survive. So that's basically justification of what usually books say. Because of the cylindrical symmetry, it's obvious that the electric field direction is radial. Right. Okay, so now I think it should be enough, that justification, right? And now I can draw. It means that basically electric field, of course, now will be a radial everywhere, something like this, right? I can draw everywhere. So now let's draw it here. So electric field at this point, for example, will be radial that way. Here I'm trying to draw a three-dimensional picture, right? So electric field, let me draw over here at this patch, will be still radial. Okay, very common place for mistakes, because students, when I ask, for example, in the exam, draw electric direction of the electric field, they draw it along direction of dA. No. Our Gaussian surface cannot change direction of the electric field. If we just justified that the electric field is radial, it must be radial everywhere. If you try to draw it next to that patch on the surface S2, it's still radial. It will be still something like this, right? So my picture is getting a little bit too much of information. And of course, the same for this dA. So it will be still radial. Because I see sometimes students getting used to the fact that electric field and area vector are in the same direction most of the time, but no. In this case, it's not that situation. Here, electric field and dA are perpendicular to each other. All right. Okay, so now, if you agree with that, then we are ready to start evaluating these integrals. First, this one, S3. I will put sort of separate, and I will write underneath explanations what I'm going to do with this integral. So first, you can see on the picture that E is perpendicular to dA. Surface S3, this surface, right? E is radial, dA is along the cylinder. 90 degrees between these two vectors. E is perpendicular to dA on the surface S3. So it means that dot product is 0, because inside of that product we have cosine of angle. So of course it will be E dA cosine of 90 degrees, and of course cosine of 90 degrees is 0. Right. So that's how we can mathematically tell that this integrand inside of this integral is 0. So of course the whole integral is 0. Right. So this whole integral, the value is 0. That's mathematical explanation why it is 0. But at the same time, you could have not guessed, you could have told that immediately. Look, you remember what is this, the meaning of this integral? It's the electric flux. Electric flux, it's a number of electric field lines crossing a certain surface. In our case, electric field is radial and it's parallel to the surface. Of course, physically, these electric field lines cannot cross that surface. So of course the flux must be 0. We discussed that these situations when we were discussing electric flux, right? So that's sort of conceptual explanation, mathematical, just because the angle between the area vector and the electric field is 90 degrees. Okay, so, all right. And then surface S2, integral over the surface S2, exactly the same story. Electric field is perpendicular to the dA, right? So similarly, this is also 0, right? Again, for the same reason. So E is perpendicular to dA. So only one integral left, right? This gives us 0. So now we need to evaluate this. And of course, this is not 0 because electric field and dA are parallel to each other. Okay, so now I can write here, so E in this integral is parallel to dA. So of course I can write explicitly this dot product. It will be E dA times cosine of 0 degrees. Two parallel vectors. The angle between them is 0 degrees. Cosine of 0 degrees is 1. So of course it will be just E dA. Okay, so now I will move to that side. All right. I will continue this line. So again, this is 0, so only this. And so now I can rewrite, so integral over surface S1, E dA. So what's the achievement after the first step in the first integral? Vectors disappeared. Here we had vector, vector. Now it's a magnitude and magnitude of those vectors. So now we don't care about their directions. Okay, so now next step, maybe I should put this. So next step, we need to use symmetry again. So look, now just imagine yourself sitting, for example, on this patch, because now we are on the surface S1, on the wall, cylindrical wall. And of course, this electric field, strength of this electric field, of course, created by this distribution of charges. Imagine yourself looking at the distribution of charges. Then, if you move yourself from this patch to the similar patch on the surface S1, for example, over here somewhere, and if you look beneath at the distribution of charges, which creates the electric field strength at this point, distribution of charges will be exactly the same. If you move yourself to this point, for example, on the surface S1, again, distribution of charges, which creates the electric field, will be the same. It means what? It means that electric field strength must be the same at any point on this cylindrical wall. Of course, directions are going to be different, right? Because direction of the electric field, first radial, it's this way, right? Okay, maybe I should show this way, right? This way, this way. So you see, directions are different, but the strength are going to be the same. And I think it's obvious, right? So now I can write additional explanation box, and I can write E equals constant. And you see, I didn't write as a vector. I wrote just E without a vector, so it means magnitude. And I will emphasize on the surface S1, on the Gaussian surface. Because we picked good Gaussian surface. So we can use this symmetry. If you picked some complicated surface, we wouldn't be able to use that. That's the advantage of using the best possible surface, right? Of course, it's not uniform. Sometimes students write electric field is uniform. No, 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 no. It's only constant since we're integrating over the surface S1, over this cylindrical surface. If you move closer, of course, electric field becomes stronger. If you move farther away from the surface, from the cylinder, of course, the electric field becomes weaker. But since we picked the best possible surface, so we can use this symmetry. So now, if it's constant, then what can be done with this constant? It's inside of the integral, we can extract it. That's, I told you about every time if we want to find electric field, we will have to extract electric field from this integral. All right, so we can write it as E integral of dA over surface S1. And now, what's the value of this integral? Again, strictly speaking, it's still calculus 3, integration over a surface. But for you, for us, we can use your high school knowledge, right? So how can we find a surface of the cylinder? It's basically area of this cylindrical surface S1. So in order to find that area, of course, you need to take circumference, 2 pi r, and times length of the cylinder, length of the cylinder. You remember how to find the surface of cylindrical, surface of a cylinder, 2 pi r times height or length. Right. So that's 2 pi and which are lots of mistakes here because students kind of remember, okay, there must be some r, and they pick just any r, and of course 50% of chance in 50% it's wrong. R small because we are on this Gaussian surface. These are small. We're integrating over the Gaussian surface, so it must be 2 pi r small times L. And as a result, finally, we're getting the value of the flux. So it will be E times 2 pi r small times L. So that's the value of the electric flux through the Gaussian surface. So we evaluated this left-hand side of this Gauss's law. Now, from the other side, it must be equal to Q enclosed over epsilon naught. Okay, now I need to erase my justifications. And what's next? Of course, very often, for example, on a quiz or on exam, at this point, I ask students, okay, find Q enclosed. And I don't know, maybe like 30% of students make this mistake. They start solving this equation for Q in terms of E. No, E is not given. We want eventually to find the electric field. So if you solve this equation for Q in, it's not wrong, but it's useless because it doesn't give us any additional piece of information. So we need to find Q enclosed using some, this picture, using some arguments, some other arguments, not from that equation. We need to find somehow this amount of charge Q enclosed, then plug it here and find the electric field. So we shouldn't be solving this equation for Q in. Again, it's not wrong, but it's just completely useless. And every semester I see that this mistake on the exam or quiz. All right, so let's find Q enclosed. Again, you remember it's just the total charge embraced by our Gaussian surface. Just physically inside of our Gaussian surface. So let's look at the picture. Of course, charge is, you see charge is distributed over the whole this infinitely long cylinder, but we're not interested in charges outside, like here, right? Q4 and Q5, we're not interested in them. So we have to do the same. Where is the charge in which we're interested? It's here. Okay, let me use blue. That enclosed charge is only here. Let me also draw it here. So this is Q enclosed. There is no charge between this Gaussian surface and the surface of this our physical cylinder. Here there is no charges. Charges are only there. And of course, You see? Just imagine it, and it's not a rocket science. So only here, this charge we must count. So how can we count this charge? Again, you need to recall that slide where we discussed that those linear surface and volume charge distribution. Right, you remember like 2 lectures ago, I think. So let's do it. Q enclosed. I think it was the third box in that slide. We need to take the, in this case, volume charge density, which is given rho, and multiply it by what? Units of rho, let me remind you. Units of rho, it's a Coulomb divided by meters to the power of 3. So what do we have to do with volume charge density in order to find charge? We need to multiply it by the volume in order to get rid of this meters cube. Right? So of course, volume of that object where this charge Q enclosed. So basically, volume of this highlighted region. Right. So which is what? Volume of the cylinder. Now you need to take the area of this base, pi r squared times the length. It's a volume. Don't confuse with the surface, right? Surface here, of course, different. It's a 2 pi r circumference times the length. But the volume, you need to take the surface of the base and times the length of the cylinder. And again, which are, so, okay, let me write first volume and then rho and pi, which are R capital. Because again, between R capital and that R small, that area is, that volume is empty. Charge is only over here with the radius R capital. Inside of the cylinder with the radius R capital. So it's a pi R squared times L. So that's the volume where the charge, enclosed charge is. Again, it's a geometry which you just need to imagine and draw nicely. Right? Because again, for example, if I take charge over here, it's not within our Gaussian surface. We must not count it. It's like these charges. Okay, so that's Q enclosed, and now we just need to take this Q enclosed and plug it over there. And the final step. So let me rewrite this here. So it will be E times 2 pi r times L equals Q enclosed rho pi r squared times L divided by epsilon naught. I'm just rewriting this, plugging Q enclosed. Okay, let's see what can be cancelled. L, great. That's what we are hoping for. When I, at the very beginning, introduced this L, it's not given, but I introduced, right? I hope that L will be, of course, cancelled at the end. Yeah, and it is. Then pi goes, and that's it. So now I have to rewrite it. E as a function of r will be equal. So now I'm writing as a function. So it will be rho r capital squared divided by 2 epsilon naught and then 1 over r. So that's the function. Let me check if I got the correct one. Yeah. So that's, let me frame it. And again, that's only correct for outside when r small is larger or equal than r capital. It's maybe looks lengthy because I'm trying to justify everything, explain everything, right? But it's not that bad. Well, if you do it a couple of times by yourself, it's not that bad. At least I remember myself, right? When I was like you in undergrad school, we like the problems like this because they are well structured, well organized. Once you understand each step, it's quite straightforward. Be careful with this area of the cylinder, volume of the cylinder. Lots of mistakes done over there because students just messed up which formulas must be used here or there. And again, as I said, definitely on the first midterm exam, there will be a problem about Gauss's law, either about spherical symmetry, we discussed that, started discussing in the lecture, or about cylindrical symmetry. Okay, so now what about the electric field inside? Okay, I will probably write it here, B. So E inside when R is less or equal than R capital. Okay, let me get it here. So now I need to redraw the picture. And what I'm going to do, I'm going to zoom in on our physically charged cylinder, because now I will have to position Gauss's Gaussian surface inside. So basically, it's this surface. I mean this object. Right. I just zoom it in. Yeah. So R capital, again, it's uniformly charged, plus 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 plus, right? So again, the same step. First, you have to pick a Gaussian surface. Again, Gaussian surface must be in the region in which you want to find the electric field. So I'm going to pick, okay, I will use solid lines. That's my Gaussian surface, of course, concentric with the physical surface. Right. So of some arbitrary radius r small. So that's my Gaussian surface. And okay, I need to probably, no, I will still so now, look guys, pretty much all what we've done over here from this point all the way to this point over here will be exactly the same. Steps will be exactly the same. Again, you will have to divide that Gaussian surface into three. Again, it will be S1 surface, S2 surface, S3. Again, you will draw area vectors, right? So this will be the patch for dA. This will be vector dA, right? Over here, there will be a vector dA. Electric field direction will be still radial, right? So again, it will be electric field, again, still electric field, over here, electric field, right? So all steps are going to be exactly the same. Not a single symbol is going to be different. So I will write exactly the same. The same way, right? In exactly the same way, we will end up at this point. E times 2 pi r. I'm just rewriting this point, right? Equals to q enclosed epsilon naught. In exactly the same way, not a single symbol will be different. So now again the same question. Let me hold you for an extra minute in order to write Q enclosed. So now the only difference is in Q enclosed. So how can we find Q enclosed? Still the same formula, rho times the volume. But which volume? Of course, now that's where the difference is. Now the volume where Q enclosed is, so this. Of course, it's smaller than that, the volume that we had over here. Because now only this amount of charge is enclosed within the Gaussian surface. So how can we find that volume? Still the same formula. It's the surface of the cylinder, this base times the height. Again, the length of the cylinder, I didn't throw it down here, L capital. Right. So what's the area of this surface? It's a pi now r small squared, because this radius is r small. That's where the Q enclosed is. Here it was r capital because that's where Q enclosed was. Now it will be rho times pi r small squared and times the length of the cylinder. So now we just need to plug it instead of Q enclosed, and we will get the expression for the electric field. Okay, let me do the last line, and the rest I will discuss on Wednesday. E times 2 pi RL equals to rho pi r squared times L divided by epsilon naught. Okay, again, pi gets cancelled, 1 r small gets cancelled, and L cancels. And we're getting the result. All right. It's difficult to write here. All right. So E as a function of r equals rho divided by 2 epsilon naught and times this r small, 1 small, or r small left. Right. Okay, so that's the function. And again, that's only correct when we are inside of the inside, and I wrote different okay. All right. This problem will be in your homework, but in your homework, linear charge density is given. Next class, I will discuss a transition between the volume charge density and linear charge density. Right? Okay, guys. All right. So tomorrow in the lecture, I will continue discussing the spherical symmetry, and here we discussed cylindrical symmetry. Right? You just need to practice it by yourself, and it's very, very straightforward. Right? And again, understanding which charge is enclosed. Come on, it's just any charge which is physically embraced by the Gaussian surface. Once you pick a Gaussian surface, you know where the charge is. So usually that's where mistakes are, in finding Q enclosed. This part and this part. That's where tons of mistakes. Okay, guys. All right. So if you have questions, go ahead. Sorry for holding you a few extra minutes, but I just wanted to finish that.